Started chapter 4, and this video will be a very short introduction to forces. A force, very simply, is a push or a pull. A push or a pull. Every force, whether it's the strong nuclear force holding a nucleus together, keeping those protons and electrons from flying apart, or the electric force that's making those protons and electrons fly apart, a force is simply a push or a pull. There are two primary types of forces. There are forces that only act when objects are in contact with each other, and those are called contact forces. And there are other forces that can act when objects are separated. These are called field forces. Can you think of any forces, F-O-R-C-E-S, field forces. Can you think of any forces that act when objects are not touching? Well, the hint is in the word field. What forces have fields associated with them? Well, we have gravitational fields. So gravity is a field force. The electric force. Protons and electrons don't have to be touching to attract each other. And then there's a magnetic field also. So gravity and electromagnetic forces, these are field forces, forces that can act at a distance. Here's a list of typical forces that we'll be talking about, and these are all contact forces, and these are all field forces. Now, just because a force is a field force doesn't mean it can't act when things are in contact. If you go outside and you sit down on the ground, you are in contact with the earth. But that doesn't make that a contact force. Every molecule in you, every bit of mass you have is attracted to every bit of mass that the Earth has via the gravitational force. It is a field force that acts at a distance, is not negated when there's contact, but it acts when things are at a distance. Now, these forces can only act when things are in contact. Typical forces are the friction force. The symbol I use for the friction force is kind of a lowercase f. You could also say capital F representing force and a little f here saying it's friction. The tension force. Tension is a force that happens in strings or cords or cables. And I would say capital T for a tension force, but you could also say capital F with a T here to indicate its tension. The normal force, and we'll define the normal force when we're talking about Newton's third law, but basically it's a support force. If you're sitting in a chair and your body is pushing down on that chair, the chair is pushing back up on your body with a normal force. Now, normal is a geometry word, and it means perpendicular. Normal forces are provided by surfaces, and the force direction is always perpendicular to that surface. I use capital N for normal forces. You may use capital N or capital F with an N here, normal force. Air resistance is an example of a drag force. There are other drag forces. Water provides a drag force when you move through water. I represent air resistance with AR. You can say F with an AR. And any applied force, if you are pulling a wagon or you are pushing a box across the floor, you are applying a force. And that force you can kind of represent in whatever way you want to that's appropriate in the problem. Sometimes it'll be a pushing force. You're pushing a box, and I would label that FP. Sometimes I say FA for applied force. So you would give that a subscript that's meaningful in the problem that you're doing. And then springs provide forces. To stretch a spring beyond its equilibrium position or to scrunch a spring together requires a force, and that would be Fs. And I don't know why I put the capital F on that one, but I do. And you should too. We will talk about gravitational forces in this chapter quite a bit. You can call that Fg. Now, another word for the gravitational force is weight. Your weight is the gravitational force of the Earth pulling on you. And we'll talk about how to calculate weight when we talk about Newton's second law a little bit later. But the way you do it is multiply mass times gravitational acceleration. So when I have a gravitational force, I often label it mg. But F with a little g there, lowercase g, would also be appropriate. Electric and magnetic forces, we're not going to talk about those in this chapter. That's way at the end of the year, and we'll talk about those in more detail when it's appropriate. In this chapter, we're going to be talking about net force, and it's going to come up a lot, and we'll go ahead and get it out of the way now. What does net mean? Well, it means total, right? Your net pay is your gross pay minus all the taxes and all that kind of stuff. Net's what's left over, so it's the total when you combine things. Forces are vector quantities, and so they add up, but their direction matters. So if you are trying to move your hand through water and you're exerting a force in this direction, well, the water is exerting a force in that direction. So the net force would be the total of the two forces, and if you're moving with a harder force than the water is, then your net force is going to be in this direction. Net forces can be in the same direction. I mean, you can add up forces that are in the same direction. If you are pulling on a box, draw a picture of the box, and your friend joins you, and your friend pulls in the box in the same direction, but there's a frictional force acting on the box, then the net force would be the sum of all of these. What is the net force acting on you right now? Well, let's think about what forces are acting on you right now. I'm assuming you're sitting down. The earth is pulling down on you. This circle will represent you. And so we'll label that force mg. Well, the chair is also pushing up on you. And we'll call that a normal force. And I'll label that n. Are there any other forces acting on you right now? Well, probably not. Probably just those two. And if you're not accelerating, if a equals 0, then the net force on you is equal to 0. And that's called equilibrium, and we'll talk about that in more detail later. So right now, the net force on you would be 0. Now, the net force being 0 does not mean there are no forces acting. There are forces acting. The net force being 0 means the forces are acting, but they're adding up to 0. And that's the end of our little introduction to forces. And we'll talk about free body diagrams next time.